So indeed, I'm going to talk about SDN controllers in the wide area network, which is a very hot topic in the industry over a couple of years now, as you probably know. The main part of the agenda, I'll be talking especially about closed-loop automation use cases, which are a very important stepping stone towards the self-driving network that Kariti spoke about in his session this morning. And in particular, I'll talk about some examples like automated congestion avoidance, where the controller sees that a link's getting congested and automatically diverts traffic away. Dynamic minimum latency path, where the controller sees that the latency's gone up on a given link and moves LSPs away that are low latency LSPs. Self-driving egress peering engineering. And also automated network self-healing, which is an automated way to drain traffic from a part of the network that's suffering a grey failure, which, as you know, is very insidious and difficult to detect traditionally. And finally, point-to-multipoint traffic engineering, which is very popular in the world of broadcast TV and market data and air traffic radar. Now, here's the sort of type of controller that I'm talking about. So it's a controller for the wide area network. And a key attribute of it is that it's a live controller directly attached to the real production network, as opposed to being a sort of offline planning tool or being a sort of passive NMS. And it's actually receiving inputs from three main sources, as shown by those blue arrows. So first of all, it's receiving information from the actual network itself. So it can see the topology of the network through the BGP-LS protocol. It can see the status of traffic engineered LSPs through the PCEP protocol. And also, it's receiving a large amount of streaming telemetry, which supplements its view of the network, how much traffic is flowing between different places and things like that. Also, it's receiving inputs from a human operator via a GUI, and also requests via a northbound REST API. And on the basis of those inputs, it's making decisions about the paths that traffic-engineered LSPs should take across the network. And it can modify the paths of existing LSPs, or it can create new ones completely from scratch as needed. And among our customers, there's two sort of main buckets in terms of the use cases that they use it for. There's one class of use case which relates to creating traffic-engineered paths to meet particular service requirements, and path diversity is a classic example of that one. And the other class of use case is actually traffic management. So people who've got huge volumes of internet traffic, terabits per second, or many hundreds of gigabits per second, expensive long-distance links, and they want to optimize the way those links are used. They don't want some to be congested while the others are half empty. They want the controller to automatically spread the load among the available resources in a dynamic way as traffic conditions change. Now, a couple of the enabling protocols that I've alluded to. The first one is BGP-LS, and so that gives the controller direct visibility of the network topology, the layout of all the links and nodes, and also link attributes. And in this example, in the diagram, we've got three IGP areas denoted by those dotted lines. And so we need a BGP-LS session into each area to absorb the topology of that particular area. Those BGP-LS sessions could go via route reflectors or could go directly to the controller. Either way, the controller is receiving information about all those different areas, and in its mind, it's stitching it all together so it sees a unified end-to-end view, and so it can successfully do path computations across multiple areas or across multiple ASs even. And among the link attributes that it's interested in receiving are things like what's the bandwidth of each link, any colors that have been configured, also known as admin groups, SRLGs that are known to the routers. And if we're doing segment routing, what are the SIDs, adjacency SIDs, and also node SIDs associated with the nodes themselves. And so, as you can see, BGP-LS is very important to give direct visibility of the network topology. And of course, it's a dynamic protocol. So if a link goes down, then BGP is event-driven. So a BGP-LS message will automatically get sent. The controller receives it. And so it knows, as well as the actual routers themselves, that a particular link's gone down, and so it can take action accordingly. Now, the other protocol that I mentioned briefly was PCEP, Path Computation Element Protocol. And that has various ingredients. On the one hand, you've got the PCE, Path Computation Element, and that's the controller. That's the thing that's doing the path computation. And then the counterparts to that are the PCCs. Those are the ingress routers of the LSPs that we're creating or modifying. And so you have a PCEP session between the PCE, the controller, and each of the PCCs. And the controller, having computed a path, sends a PCEP message to the ingress router saying, right, I want you to set up this new path. This is the name of it. This is the sequence of hops that I want it to follow, and so on. And the ingress router then responds by actually instantiating that path. It could be doing it using RSVP signaling, or it could be doing it using segment routing. And there's PCEP extensions to deal with the segment routing case. PCEP's, very importantly, is a two-way protocol. And so as well as it being used by the controller to send orders to the ingress routers, in the reverse direction, it's used as a way of confirming that what's been requested has indeed been set up, and also to signal changes. So if an LSP goes down for some reason at the network layer, PCEP will signal that to the controller, so the controller knows about that and can take action. Now, closed-loop automation, we haven't seen much of that in the world of networking so far, but now it's coming in with the advent of these controllers. Now, this diagram at high level, if you actually ignore the labels, applies to many areas of engineering. It could be the cruise control on a car or the air conditioning system in a building. And the key point is that you have a feedback loop which actually feeds back to the controller and allows it to tune what it's actually doing. And so what you've got is the user requirements, or the user intent, as it's fashionable to call it today, coming in from the sort of top left. And then you've got the controller, which actually takes those requirements and actually imposes those onto the network. But as you know, the network's not a static entity. It's more like a living creature. And so it's subjected to disturbances. You've got links going down. You've got traffic patterns changing, threatening to cause congestion. And so what's very important is that the controller has a feedback loop where it can actually see what the network is doing now. And the protocols that I mentioned already are a key part of that feedback loop, as you saw, PCEP and BGP-LS. But also the streaming telemetry plays a very important part. And so the network nodes are streaming all sorts of information to the controller to give it a better view of what's happening in the network currently. And that includes aspects like how much traffic is traveling on each physical link, how much traffic is entering each traffic-engineered LSP at the ingress, what's the current latency on each link, which the routers are measuring by sending probe packets to each other and reporting that via the telemetry. So all of that information acts as the feedback to the controller, and so allows it to tune the paths of LSPs that might already exist in the network that it's created previously. And so that's how we close the loop, and that's how we achieve the closed loop automation. As I say, a very important stepping stone towards the self-driving network. Now, let's have a look at some use cases along these lines. This is one of my favorites, actually. So this is dealing with congestion automatically. And so the controller, as I say, is monitoring how much traffic is on each physical link. And it knows that that link coloured in red in the middle of the diagram is actually approaching congestion. Maybe it's getting towards a dangerous threshold. And it knows which LSPs are using that link because it's probably set them up. Even if it hasn't, PCEP reports their existence and their paths to the controller. And so the controller can actually work out which LSPs are best to move away to ease the congestion. And in so doing, of course, it has to make sure that it's not causing congestion elsewhere. When it works out which ones to move and when it's computed their new paths, it sends the new paths to the respective ingress routers using PCEP, and they move the LSPs in a make-before-break manner. And so in that way, we succeed in easing the congestion. Now, this type of traffic engineering, sometimes it's known as tactical traffic engineering, people have been doing manually. And it can be quite, cumbersome, because if it's a human being doing it, then they've got to, first of all, realize that a link's getting congested. Then they have to work out which LSPs to move, and then they have to do it in such a way that not going to cause congestion elsewhere. And then they have to go onto the ingress route and perhaps put in some, strict or loose hops to, divert the LSP in the way they want. It's quite, sort of error prone. And after a few months of doing this, you can end up with a rat's nest of LSPs which have been pinned around the network in various different ways. And the reason why you pinned some of them might have gone away, but it's quite difficult to unravel the whole thing. So having a controller do it fully automatically, of course, makes life a lot easier. In a similar vein, I'm coming on to the topic of latency, lowest latency paths. So as a sort of preamble to that, when it comes to cost functions, a controller can have a variety of cost functions for different types of LSP. Typically, the default is the lowest IGP metric path that meets other requirements, such as bandwidth requirements or path diversity and things like that. In this network, where we're showing the IGP metric on each link in blue, as you can see, the lowest IGP metric path between X and Y is shown by that blue LSP along the south side of the network. On the other hand, the latency on each link might be different, and so the latency is reported to the controller, as shown by those red numbers, and actually the lowest latency path between X and Y is shown by that red arrow. And so, indeed, the controller can compute the lowest latency path if you want one, because it knows the topology of the network, and it knows the latency of each link, because that's been reported via telemetry from the routers. And so it can be a dynamic thing. So the controller, if it sees that the latency's changed, a classic case is if you have a fiber cut and in the transmission layer there's protection kicking in, might be a transatlantic link where the latency goes up by several milliseconds. The controller realizes that the latency's gone up, and so it automatically reroutes all the low latency LSPs that had been passing through that link. As you can see, the red LSP has been moved by the controller in a make-before-break manner, so the traffic's unaffected during that move of the LSP. A bit like the previous example, doing it manually is quite painful. You have to realize that the latency's gone up. You have to work out what now is the lowest latency path. You have to go onto the ingress router, put in a new set of hops to steer the LSP in the way you want, the now current lowest latency path. And having it done by the controller makes life a lot easier, as you can see. Now, another interesting example, in this theme of automation and self-driving is automated network self-healing. Now, if you've got a sizable network, sometimes you can encounter so-called grey failures, and these are especially dangerous because a grey failure, by its name suggesting, is isn't black and white. It's something in between. Something is sort of broken, but it's still sort of working. And actually pinpointing these failures can be a bit like looking for a needle in a haystack sometimes, because the effect of it might be that a proportion of the traffic going through that faulty node or link is being affected, but things like BFD or IGP hellos aren't picking that up because the packet loss rate is not high enough to actually lose 3 consecutive hellos, for example. Now, there are health monitoring systems, for example, HealthBot that Kriti mentioned this morning, Appformix, both of those from us, which are good at detecting these types of grey failures. And so the way the workflow shown on the slide works is that once one of these systems detects that you've got such a grey failure, it's using that by looking at streaming telemetry data pertaining to either node internals or attributes of a link, like obscure error statistics like L3 incompletes and things like that. Once it's determined that the link's unhealthy, it sends a REST API call to the WAN controller, which is called NorthStar in our case. And it says to the WAN controller via this REST API call, this link, L1 in the example, I want you to create an immediate maintenance interval on that link. And what that means is that the WAN controller automatically diverts away all the LSPs that are passing through that link. It recomputes the paths, sends a new paths to the ingress routers, as shown in this example. And so now the traffic's been automatically drained away from that faulty link. And so you're free to investigate in more detail. You know, maybe you have to clean a fiber or change a pluggable optic or something like that. Traditionally, you know, as I mentioned, detecting these faults is quite tricky, and then you have to work out how to take action. So having it happen automatically helps a great deal, and it's another good stepping stone towards the self-driving network, as you can see. Now, again, in the theme of self-driving egress peering engineering, the way I've been talking about the controller so far is, you know, talking about network internal topology, you know, your own WAN, you know, going from your edge routers inwards. Another interesting layer to look at is the peering layer, of course. And so we can illustrate that here, where we've got your own WAN, which is the larger cloud at the bottom of the slide, and various other networks. You're peering with different, you know, ASBRs belonging to different ASs. And suppose in this diagram we focus on how you're sending traffic from your network, from your various ingress points, through your peerings to prefix X, which might be several AS hops away on the internet. And the controller, what it's doing in terms of data gathering, is using IPFix reporting from each PE router to see how much traffic each PE is sending to each prefix in the internet table. And what it is doing is deciding which egress link on which egress ASBR each ingress PE should use to send traffic to that particular prefix X. And it's doing that on the basis of the data that I mentioned, and also a cost function, which is based on the cost to reach a given ASBR from the point of view of a given ingress PE, the cost of using each peering link in itself, the degree of utilization of each peering link, because the controller wants to make sure that you don't congest you know, one of the peering links while the other ones are still relatively quiet, and also, you know, user-defined preferences, because you might have your own you know, sort of order of merit of using different peering links to reach a particular destination. And then, if needed, it can swing the traffic across. So from the point of view of PE2 sending traffic to prefix X, whereas before it was using the ASBR on the left-hand side of the slide, it's now swung it across to ASBR2, and it's using the peering link to ASBRF. A flavour of how it's actually achieving that, one of the ingredients that we use is something from segment routing called PSIDs. And so this ASBR in the example, your ASBR on the left-hand side, has allocated SIDs for each of the peering links that it's got to the ASBRs which it's peering with. And those are actually reported to the controller via BGP-LS. So BGP-LS, as well as reporting SIDs from the internals of the network and the internal topology of your own WAN, is also reporting these sort of extensions to your network, these peering SIDs. And what it means in the forwarding plane in this example, if you look at the SID to ASBR-C, that's got a value of 200. What it means is that if an MPLS packet arrives at ASBR, your ASBR-A, with top label of 200s, that ASBR simply pops the label and pushes the packet out on that particular peering link. And so, you know, from a remote source, by virtue of that label that you've put into the label stack, you're controlling the fact that when the packet arrives at this ASBR, it pushes it out on that particular peering link and not any of the other ones, you know, that it has. So that's one of the key ingredients. The other aspect is that the controller is actually installing on the ingress PE, PE2 in this example, a segment-routed sequence of hops, which consists of, if you want in the most fancy case, a sequence of hops to steer the packet in a particular way across your own wide area network, a traffic engineered path. But then the final label in the stack is the label required to actually take it on the final hop from your ASBR to the peer ASBR. And so, in effect, the controller is having PE to send the traffic to the ASBR that it's chosen, and furthermore the egress peering link that it's chosen. And so that's bringing greater level of automation to the peering layer of the network, as well as the sort of internals of your own WAN network. Now, another interesting topic, which I alluded to at the beginning, is point-to-multipoint traffic engineering. This has become very popular over the last few years for mission-critical multicast traffic. It's used a lot in the broadcast TV industry for professional broadcast television. It's used a lot for IPTV distribution, and I know there are people in the room using it for that, and also cable TV distribution. And what people often do, in fact, they're using point-to-multipoint LSPs to achieve it. These are traffic-engineered LSPs. And the reason they use those is that you can perform admission control, you can have bandwidth reservations, and so you know that for this mission-critical multicast traffic, you're not going to have contention in the middle of the network and be dropping the packets halfway through their journey. And the other thing that they use for the ultimate in resilience is to have diverse pairs of point-to-multipoint LSPs, which you can see in the diagram. And so what you've got is the red point-to-multipoint LSP and the blue one. And the controller has done a diverse path computation of this pair of point-to-multipoint LSPs, such that they are indeed diverse. They don't share any fate. They don't have any links or nodes or SRLGs in common. And what people actually do with these point-to-multipoint LSPs often is to do what's known as live-live, where you're deliberately sending two copies of the of each packet into the network, one into the red point-to-multipoint LSP, one into the blue, and then at each receiving location at the application level, normally under normal circumstances you're receiving both copies, but then you're reconciling and just discarding the one you don't need. But if something breaks in the network, then at most one of the P2MP LSPs will be affected and not the other. So at the application layer, you're still receiving a continuous stream of packets on one P2MP LSP or the other. So at the application level point of view, you don't notice any glitch or anything like that in your traffic flow. I mean, a use case for this that's used in several countries nowadays is for digital terrestrial distribution or distributing TV signals to satellite head ends. In some places, it's even used for air traffic radar, which is the most mission-critical application I can think of. You're actually taking air traffic radar signals from the radar collecting stations, where you've got those sort of spinning antennas, and sending those to redundant air traffic control centers. And to do that, you're using the point-to-multipoint traffic engineering with the path diversity. And so the key thing is, the controller is doing this diverse path computation and sending the result via PCEP to the ingress routers, because there are PCEP extensions for point-to-multipoint LSPs that allow you to actually do this. Now, this is showing a screenshot of a point-to-multipoint LSP overlaid on the WAN topology. So the sort of general topology that you can see has been acquired from the network using BGP-LS. That's how the controller knows all the names of these nodes, because that comes from BGP-LS. Those node names originate in ISIS and are automatically exported into BGP-LS. The layout of all the links, again, coming from BGP-LS. And then the point-to-multipoint LSP is displayed overlaid on that. So the ingress of that is you can see the node with the small sort of green square around it, that denotes the ingress. And you can see the branches of this P2MP LSP, with that sort of orange color code. So you can see, where this P2MP LSP starts and where it branches off to and what are the destination nodes. And this is a live view because this is coming from PCEP reporting from the network. If you compare this to actually looking on the router CLI, you'd have to look on the CLI of the ingress router. You'd be looking at strings of IP addresses for each branch of the tree, and you'd have to sort of correlate it with your network map and sort of try to understand what it all means. It's much easier just seeing it in front of your eyes on the GUI of a WAN controller. Now, this is a view of the P2MP LSP overlaid on the actual network topology, but you can look at that same P2MP LSP in a different view And this is more like a sort of logical layout. It's more like a metro map where the ingress of the P2MP LSP is on the left-hand side of the diagram. And you can see it fanning out to all the various egress nodes from left to right across the diagram. So you can see much more easily which nodes the P2MP LSP serves. And as I said, this is a live view. This is coming from PCEP. This isn't a sort of theoretical view of the P2MP LSP. It's what it's actually doing in the network at this moment in time. Now, this, I mentioned, is used in the broadcast TV industry. A good use case is Sky. So they've deployed our NorthStar WAN controller for exactly this purpose. And so this is a screenshot of their network. It's acquired via BGP-LS. You can see a mixture of different sizes of links, 100 gigs in the core, n times 10 gigs towards the edge of the network. And that's a real-time topology view acquired from BGP-LS. And then they can set up LSPs. They can monitor the paths of LSPs. So this is showing a point-to-multipoint LSP as reported via PCEP and shown in the GUI of the controller. And as I mentioned, you can set up LSPs as needed, either via a GUI or via REST API calls, including diverse path setup requests. So this is a very good example of an SDN WAN controller being used in real life in a very useful use cases. This brings me more or less to the end. Finally, some useful references. In particular, if you're interested in knowing more about the nuts and bolts of PCEP and BGP-LS, we did a deep dive webinar in the slides, and the recording is posted. So that really looks into detail, packet dumps, looking at what all the fields of a PCEP packet looks like when a controller requests an LSP setup, what the replies look like, and things like that. So if you're really interested in going into the details, I recommend that one to look at. So that brings me to the end. Thanks a lot for your attention. Any questions? You can ask now, or I'll be around during the breaks.
No?
Okay, thanks a lot for your attention.
Give Julian a big applause.